So here's an overview. I have been interested in group representation theory for a long time, and that's a type of generalization of Fourier analysis. And so in this talk I want to start with the group representations of the dihedral group and show that they lead to edge filters. Then I compute second-order moments of such edge filter vectors. And then I apply the Perron-Frobenius theorem that tells you that if you have a matrix which is positive, which means all the elements are positive, then the first eigenvector is has only positive elements, and it's somehow related to the mean. Then I project the data along the first eigenvector, and then I show that this will lead to a group that is called SU11. Then I use the radial part of the projection to measure the distance to the mean. Then I use SU11 and its Fourier transform, this is this Miller-Fock transform, to analyze the distance distribution. And then I apply this to natural scene statistics. So when you can ask, why should I do that? The answer is that, as I mentioned, I have worked with these group representations for a long time, and this first group, the dihedral group D4, that's very simple and very well understood, and then you can implement more or less the textbook results into a program. The SU11 part is, I mean, mathematically there is nothing new here, so you can read it in the textbooks. The SU11 part is more or less the easiest part of the nasty type of groups. So when I looked at what has been done in signal processing and vision science, then I saw nothing. So the conclusion is, first, nobody has done this, so this is new. Or the other alternative is that somebody has done it and it didn't work, or abandoned it. So the only way to find out is to do it and see what comes out. So what I want to do is I will give a hand-waving overview over these steps. And then, depending on how much time I have left, then I will go into some nasty formulas, which are probably best read from the book. So, okay. So, I start with patches of 5 by 5 pixels. And 5 by 5 is simply the smallest patch where all the relevant cases turn up. So this 5 by 5 patch is invariant under 90 degree rotations and reflections on diagonals and axes, and these transformations, they define the dihedral group D4 of the symmetry transformations of the square. So, next step. If we look at the orbits of this group, so start with one point and apply all the group elements, then in this case here you get 4 orbits which consist of 4 points, and then you can generate an 8-point orbit. So that's the reason why the 5 by 5 is the smallest case, because that's the first time you can generate an 8 orbit. So then you go to your textbook, apply this Fourier transform for this D4 group, and then you find out how to break down functions on these orbits into smaller components. And one of the components that you get in this function space is defined by type of edge filters. So you have this collection of 2 minus ones and 2 plus ones, and the theory tells you you always have to take them in pairs. So that's the result from the dihedral representation theory. And then it shows you also that the magnitude of the two filter results, that is somehow invariant under all these transformations. And then you get one filter pair for these 4 orbits, and you get 2 filter pairs for the 8 orbits. So it makes 6 edge filter pairs that you can generate on this 5 by 5. And so we take 1 pixel, compute our 6 edge filter pairs, and compute the magnitude. And so now in each pixel we have a 6-dimensional vector. And because it's magnitudes, so then all the elements in this vector are non-negative, right? Okay, so now we have an image where each pixel has a 6-dimensional non-negative vector here. Then we want to compute somehow the local statistics of these 6-dimensional vectors. And so we compute local averaging over these outer products of the 6-dimensional vectors. And so we get at each point a 6 by 6 matrix. The matrix is symmetric, and it's positive, symmetric, definite, and all the elements are non-negative because all the vector elements were non-negative. So next step is that we apply the Perron-Frobenius theorem, and this tells you that if you have such a matrix, then the first eigenvector has only non-negative elements. So compute this. Then we compute the 6 eigenvectors of this matrix at every point, and we expand the vector in this point in this eigenvector system. And because the vector itself was non-negative and the first basis vector is non-negative, then the result must also, the scalar product must be non-negative. And if it's positive, then we can divide the components 4 to 5 with the first one. So we have now 5 ratios. And if you think of this geometrically, then what you have in this 5-dimensional space, or in the 6-dimensional space, is a type of a conical structure, where the first element, the first component, describes you the axis of the cone, and then the other components must be limited because of the geometry of the projection. So then you have a description, and to make it simple here, I only take the first 2 of these ratios, because that's the interesting part. The rest is technically a little bit more complicated, but nothing new or theoretically there. So we take the first 2 ratios, and then by this cone picture they must be elements of a disk, and the radius of this disk is capital R. And then we introduce polar coordinates on the unit disk with the rho of x and the cosine theta. So the intention is now that somehow the rho describes the distance from the mean, the axis, and then the angle that describes the relation between the 2 coordinates. So if you are familiar with color theory, then it's very similar to color spaces. where the radius in, or the length of the vector, this first eigenvector, that is somehow the intensity. Then if you project the color to your chroma disk, then you have saturation, which describes purity of the color, which is the distance to the gray value. And then you have an angle which describes radical improvement. So this is the basic idea here. It's the same type of reasoning here. Okay, so now we have reduced the whole thing to the unit disk. And then comes the next hand waving step. We introduce a geometry on this unit disk, and we say that we introduce the special unitary group 1,1 on this unit disk as the symmetry group. So why should we do this? That is also partly motivated by the type of color thinking. Because if you think of saturation, then if you go to the border of your saturation interval, it becomes purer and purer and purer. So the relation between saturation on your interval is not linear. But if you come to the border of the saturation thing, it's infinitely saturated. So somehow it's a different geometry than only polar coordinates. And that's what is more or less described by this SU11 geometry. And then, as the last step, when you look at harmonic analysis of these geometries, then you see that the angular thing, that leads to something that is related to Fourier series, so we skip this. The really difficult part is the radial analysis. So now you want to make a Fourier transform on functions that are defined on this radial interval. And that's the Mailer-Fock transform. So then if you have somehow come so long, then you can think of, okay, now we understand what we should do, and is it somehow useful, or what comes out? So what I did was, there is a database of natural images from a savanna type of environment, and that's collected because it's thought of that our ancestors grew up there, and somehow the statistics of this type of environment must have some type of relation to the visual system of our ancestors that lived there in this environment. So they took these images, and then they were very careful of calibrating them, and then converted it to different coordinate systems that are useful related to visual perception. So I selected in this case the M channel, which is somehow related to, you can think of a green type of thing, which is more or less related to intensity. So this is a typical image of these environments. And then I selected the center patch, because that's where most of the interesting things are happening there. And then I computed the coordinates, and then the hyperbolic tangent of the radial coordinate, that is the thing that you are investigating. So this is the patch, and then if you do all these transformations and calculations, then you end up with such an image of the radial component there. And then you do this, and if you have a patch where you have enough data, so I mean there are flat patches, so then you can forget that. So I selected the patches, the images where you have enough data that you can make some statistical calculations there. And then I fit the distribution of these row values. And the first thing that you can see here from the left picture there is you can expect that the values that you get that are non-trivial are probably very small, because that's the mean that is typical. And then there are some outliers, so you have something that is really far away. And previously, when I looked at image statistics of these type of data, then I found out that very often the generalized extreme value distribution gives very good fittings for this type of magnitude data. And that's the same thing that I found here too. And then you have this probability distribution, and then you can do the Mailer-Fock transform of these data. And then you can investigate what is happening with the Mailer-Fock transform. And so one thing is when you come from signal processing, you take some type of low pass or high pass filtering. And the thing that I did here was that I did the transform, and then I truncated the transform, and then looked at the length of the transformed vector, and then looked at the original patches, what is then somehow the visual equivalence or the meaning of these things. So that's what I told you. So I compute a sampled Mailer-Fock transform, truncated it, and then compute the length of these truncated vectors in the coordinate system and in the metric that you should use in this Mailer-Fock space. And so these are three different classes. So the first one are things where the transforms are very small, then medium, and then very high values. And then if you look at the real tangent hyperbolic images there, then you can see that for these low Mailer-Fock values, we have very rough or very smooth structures there, very little variation. In the middle, then you have these type of regions where you have low variations and high variation, and then it's more or less pure noise here. And that's not so easy to find, to think about when you see the original images, because these in the middle, for example, there is very little structure here, but you can see there is a structure in this projection business. Okay, so that was more or less the the distributions here. So the statistics behind them. So that was more or less the story. And if I now spend a few minutes on some technical points here. So what is the Mailer-Fock transform? The group SU11 is a group of elements with 2 by 2 elements, and as they are complex, and a squared minus b squared is equal to 1. They operate on the unit disk with these Möbius transforms. Now it becomes nasty because you have to find out how these transforms are operating. And so that's what you find in the textbooks. And then you'll find out that you can write every element as a product of a rotation matrix and this hyperbolic rotation. And the thing of the Mailer-Fock transform, why it's so special, is that these transformation of the coordinates, you have to find out what is the exponential function of this. So what is transforming nicely under these type of transformations. And already these transformations are very non-intuitive. So these are the things, how they are defined. And the exponential type of function, that are these associate Legendre functions. And they fulfill this property that you can factorize the group product into products of the functions. So they are diagonalizing these type of operations. Okay, that's how they look. And you have a whole interval of these things, and you have also an order M here. So it becomes a little bit messy. And then the Mailer-Fock transform tells you that there is a pair between the original function k and the transform, and then you can have an inverse transform in the right coordinate system. And you have the same type of theorems like in the Fourier transform, that they preserve scalar products, for example. And now you have to implement these things. And so that's not true. So you have to calculate infinite intervals, you have to find out samplings, you have to find out how to compute the function values, and so on. So, okay, that takes a while to do this. So what have we learned from this whole thing? So one thing is, of course, that you can go to the textbook and you can find all the tools and all the results from harmonic analysis. So you find this Mailer-Fock transform, you can find the transform, the lengths and so on. Sampling is, the implementation is not so easy. I think it's useful for feature extractions, and there's a lot of work to be done when you want to really use it in practice. Thank you.
Thank you. Edges in natural images are not necessarily, horizontal or vertical or diagonal, but this is the symmetry that is preserved by the dihedral group. So have you any views on how this, whether this works better for certain oriented edges, or doesn't that matter?
The question with the dihedral group is that you have to think about very, very small things. So 5 by 5 pixels is not very much. And and it's also statistical. And probably it's, or certainly it's not very useful for looking at chessboard pictures. So, and that's the reason why it's probably useful more for type of natural textures. So, if you want to understand why all these type of filters come up in the visual system, then probably the risk that you see a natural texture is much higher than that you see type of Mondrian pictures all the time. So that's.
Can you recall, please, from what comes the number, the dimension 6?
The 6 comes. So you have in this 5 by 5, you have 4 orbits with 4 points, which gives 4, and then we have 1 orbit with 8 points, which gives 2 H pairs. So that gives 6 H pairs.
One more question, yes?
Thank you. Could you extend your work to JPEG block size?
Yeah. So all the choices I made here was that I tried to find the smallest case where the typical cases come in here. So 5 by 5 is simply the first one. I could extend this to any patch size in the grid, and I could also use more than only the one angle, simply by having the others also. But there is fundamentally, theoretically, nothing new.
One small question that I have. When you were using probability distribution, the family of probability distribution to model, you used the generalized extreme value.
Yep.
Any reason for, or any argument for?
Yes, the reason behind these extreme value distributions is that they are somehow similar to the law of large numbers.
Mm-hmm.
So if you take the mean of random variables, then the limit goes to the Gaussian distribution. If you replace the mean by the maximum, then you can show that if these things converge to something, then it must be one of these generalized extreme value distributions.
Thank you. Thank you again.